Okay, so the first defect of vision we're going to look at is myopia, which is just another word for short-sightedness. I will usually use the word short-sightedness, but you need to know if you see that word in an exam that it means short-sightedness. Okay, so myopia. So someone who is myopic would have short vision. What we mean by short-sightedness is they can see things that are a short distance away, i.e. their near point is okay. So they have the normal near point of 25 centimeters, but the problem is they can't see things that are far away. So their far point should be infinity, but it's not. Okay, it's going to be closer than infinity. So in the case of this person, it is 4.5 meters away. Now the problem here is that if we did have an object that is at infinity, the rays of light would enter the eye and they would be refracted in such a way that they wouldn't meet on the back of the eye, which means the image would be blurry. Okay, it'd be out of focus. The problem there is that the lens can't be made thin enough, or another way of looking at it is that the eyeball is too long, essentially, in this case. Okay, so eye is too long can be seen as a problem here. So what we want to do is we want to fix this. Okay, we want to use a lens that will allow them to focus on light that comes from infinity. Okay, and how we do this is we use a diverging lens. Okay, so we want light that is coming from infinity to be focused by the eye, but what we know is it can't focus on light that's coming from infinity, but it can focus on light that comes from 4.5 meters away. So it can do this. So what we do is we use a lens in such a way that it diverges. So we're going to have to use a diverging lens here. The light before it enters the eye, so that that light appears that it's coming from that person's defective far point, which is infinity, it's 4.5 meters away. And then if the light enters the eye like it comes from 4.5 meters away, we know that the person can focus that. So this is how we fix short-sightedness. We use a diverging lens. Now, if we look at the maths behind that, then we want them to be able to focus on an object that is an infinite distance away. So our value for u is infinity, okay? But we need that light to appear like it's coming from 4.5 meters away. So by that we mean the image that the eye sees should be 4.5 meters away. However, if we notice, it's on the same side of the lens as the object is, therefore v should be negative. And in fact, a key thing to remember for all corrective vision questions, v is negative. Okay, and we want to find out what focal length of lens we should use to fix this. So we're trying to find f. We write out our equation, okay, our lens equation, just the same one we use, doesn't matter that it's for corrective vision here, and we put in our values. Now 1 over infinity minus 1 over 4.5 equals 1 over f. 1 over infinity, well, the bigger a number we divide by, the smaller that gets. So 1 divided by 2 is 0.5, 1 divided by 20 is 0.05, 1 divided by infinity is 0. So we can just ignore that term in there, which means that we then should work out that f is minus 4.5 meters. Okay, the minus sign confirms to us that it is a diverging lens that we use there. Okay, now here's the tricky bit. Brilliant. These lenses have fixed the person's inability to see things far away, but like most things, there's pros and cons. Us putting that diverging lens in there will not just fix their defective far point and make their far point infinity like we like, but it's going to change their near point as well. So what we want to see is, okay, before they were able to see things that were 25 centimeters away, they had a normal near point. But what effect does wearing these glasses have on that? So what we want to find is really what's the furthest an object could be away. So we're trying to find you when they're wearing the glasses that have a focal length of minus 4.5 meters. so that when they're wearing those glasses, the light is going to appear to come from their near point. Okay, so if we look at this little diagram, it kind of explains it. So before, when they're not wearing glasses, if we ignore that lens for a second, they can focus on light that comes from 25 centimeters. Brilliant. But now the light that comes from 25 centimeters isn't going to look like it comes from 25 centimeters because of the diverging lens. It will now appear to be coming closer, and the eye can no longer focus that. So we want to find out, where does this object have to be placed? So what is u, the object distance, so that when that light passes through the corrective lenses, it's going to diverge, but in such a way that it appears to be coming from the closest point that that person can focus on, which is 25 centimeters. Okay, so our inputs into the lens equation to find out the negative effect it has on their near point is the focal length is the same as we worked out the focal length to be that's needed to correct their vision. We want to find out where the object is, so we're looking for u when it appears to be coming from their near point. So v is minus 0.5. Remember, v always negative for corrective vision questions. Put that into our equation, do a little bit of rearranging and working out, and we find out that u is 0.265 of a meter. Okay, so it's fixed our 4 point. They can now see all the way to infinity. It's slightly made their near point worse. They used to be able to see things that were 25 centimeters away. Now they'd have to move it a whole 1.5 centimeters further away. It's no real negative effect there. Some people with stronger prescriptions, there would be more of a negative effect, and you may find people have to take off their glasses so they can see things that are close up.